Okay, so welcome everybody. Welcome to good morning, everybody. Welcome to this first live seminar in this by Zoom. I would like first of all to thank Patricia Conde Muíño for accepting this invitation to give a seminar. She's, as you know, responsible for the Atlas activities in Portugal, and today she's going to talk about the Forward Physics program at Atlas. Patricia, please.
Okay, thank you. So you have seen me. I will disconnect the video because there can be some unstable connection from time to time, and so I ensure the quality of the sound better. So okay, thank you for providing me with this opportunity to give the seminar. I will be talking today about a part of our physics program that is not so well known. That is how we can use the forward proton tagging in Atlas to prove a standard model and also search for new physics. So, okay. So why diffracted protons? What do I mean by that? The kind of events we will be talking about today are those in which we have something produced in the central detector, such as in this event display, we have 2 photons here. And then we have 2 diffracted protons that go through the beam pipe, and they are reconstructed or identified very far away. In some dedicated detectors that you see here, and they are about 200 meters far from the central detector, okay? So the kind of physics we can do with diffracted protons extends over a large range of cross sections, and that means also that requires different volume of integrated luminosity to be studied. So we have processes with huge cross section, like the total production cross section or inelastic and elastic components of this cross section that we can study with alpha. And we have also process with high cross sections such as single or double diffractive events and differential distributions in this kind of events and other processes of this type. In the medium range, we have central exclusive. So, okay, actually have a drawing of this kind of event. So up here we have single diffraction, and the forward proton tagging is important to distinguish single and double diffractive events. In the medium range cross-section, we have central exclusive production, in which we have 2 protons, and all the energy is used in this central production, and there is no other activity in the event. These are very interesting events, and we'll talk about them later. In the high range of cross sections, in the lower range of cross sections, sorry, that require high luminosity, we have processes such as the quartic gauge boson couplings. And these diffractive events allow us to study, for instance, photon-photon WW cross-section interactions in the, or with a pair of Z bosons produced in the final state, or photons, and this allowed to measure triple and quartic gauge boson couplings with quite some precision. In addition, we can search for new physics, and I will talk about today of 2 different topics: flavor changing neutral currents in top quark production, and also searches for dark matter as kind of processes that are interesting to study, but there are a wealth of theoretical predictions that could be studied in searches that could be done with forward detectors. So to start with, let me explain you which forward detectors we have in Atlas. We have 2 sets of detectors. This is the Atlas detector, and about 200 meters from there we have the AFP, Atlas Forward Proton Tagging detectors. And a little bit farther we have ALFA, the absolute luminosity detector. So the first one I will talk is ALFA. It's also the one that has been built for a longer time. It was designed to measure, ALFA stands for Atlas Luminosity Detector, and it was designed to measure the absolute luminosity. And as you can see in this image here, it's made of fibers, scintillating fibers that are collected and read out by photomultipliers, multi-anode photomultipliers in the upper part, and they are inserted in a Roman pot that gets very close to the beam. This is the region where it moves and it gets really close to the beam. So the alpha detector can measure scattered protons at millimeter distance from the beam with resolutions in X and Y of the order 30 microns. We have two detectors, an upper one and a lower one, and some overlapping detectors that allow relative alignment between the two stations. As I said before, they are done of squared scintillating fibers, and this is one of the reasons why we are working this detector. We were asked to participate because of our expertise in optical fibers and aluminization. The fibers are aluminized in body and top, and we did aluminization at the top here in Lisbon, as you can see here in this image. This is one of the pictures taken here in the LOMAC lab. So the scintillating fibers are staggered in layers. I read that by photomultipliers, as I said before. And here we can see, there inside the Roman pot, we can see an image of the Roman pot closed, overimposed with a profile of the beam as taken with the alpha detector. You can see this goes in the vertical direction. Alpha cannot take data at high luminosity. It was designed to operate with special optics and very low luminosity. Here we see so the expression of the luminosity at the LHC. So we have the number of protons per bunch, the number of bunches, the revolution frequency. Down here we have the emittance and beta star, and this is a factor that takes into account the crossing angle of the beams. So alpha runs at high beta star. That means this beta star parameter is the focusing of the beam close to the interaction point. And the wide, when it is large, it means that the beams are flat and wide. And we take data at 90 meters beta star, or well, actually up to 1 kilometer. So. Okay, the detector control system is another of the Portuguese contribution to the alpha detector. It is the system responsible for the safe operation of the detector and monitoring, and also to help recover problems in the detector. This is the panel that we can see normally in the control room for the operation of alpha. Okay, part of the panel. Through this panel, one can control what is the status of the detector and take actions in case of problems. And is currently, I mean, we are the fully responsible for the DCS since many years. The other detector, forward detector, I will talk about today is the Atlas Forward Proton Tagging detectors. And with this, we have, so they are placed a little bit closer, and there are two arms on both sides of the interaction point, and they have different detectors. On one hand, we have silicon tracking planes in the first Roman pot, and in the second one, we have silicon tracker and time of flight detectors. The real thing is shown here. Here you can see the tracking detectors. They are slim edge 3D. They are made of slim edge 3D Atlas IBL pixel sensors with a resolution of 6 micrometers in X and 30 micrometers in Y. And they can also provide triggering with a majority vote 2 out of 3, for instance. Here we see already the time of flight detector that is made of quartz bars that are at the Cherenkov angle with respect to the direction of the protons. They have a groove in this, here it is not very clear, it's a cut in this direction to maximize the collection of light. And they can provide, they have already provided time of flight measurements with 26 picoseconds resolution. They are read out by photonics multi-channel plate photomultipliers, and they are inserted horizontally within the Roman pots. And here we see an image, so they move in this direction, and this is, okay, an image of the Roman pot overimposed with a pattern, a typical pattern we will see in a diffractive event from data taking. So the detector control system of the AFP detectors is another of the Portuguese contributions. We are currently co-leading the group and have responsibilities in the Roman pot movement and vacuum and cooling controls. This system is characterized by a very large variety of subsystems that have to be controlled. They include the central part that is in the Atlas cavern, and also the part that is 330 meters distance, okay? And the detector control system is done with a finite state machine that it's like a tree of processes that have different states. I will not talk too much about this because you will have a seminar in the near future about all these control systems. So I moved to the status of AFP. AFP was designed to be installed in a staggered, it was installed in a staggered procedure, and the first arm was installed in 2016 in the long year, end of the year shutdown. And then the next arm was, and the time of flight detector was installed in 2017, also in the year-end shutdown, technical stop. The first year of operation showed that we had some problems in efficiency, and these were identified to come from the photo multipliers that were breaking down in vacuum, and they were not working correctly, in addition to the radiation damage problems. Despite the very low efficiency, we have observed very good timing resolution, the order of 20-25 picoseconds per proton. This, for the round 3, the detectors will be, they will be improved, and we have new time of flight detectors that not only will have the PMT will be placed out of vacuum, and we will have a light guide that moves the guide to the PMT. And this ensures the long lifetime of the PMTs. And in addition, we will have a new Pico TDC that will improve the timing. This Pico TDC is the dominant contribution to this timing. It had currently 17 picoseconds resolution, and now it will be improved to 3 picoseconds. So we will be able to improve this timing resolution in the future. So we'll move now to the physics part, and I will talk about some of the measurements we are going to do with, we have done already with ALFA, and some of the measurements we will do in the future. With ALFA and AFP, sorry. And so I will start with the total cross-section that you see here. If we see the, where is the Higgs? The Higgs, I think, is here. Okay, this is the Higgs production cross-section, so we are really a few orders of magnitude above that. So in ALFA, we can measure total cross-section through the elastic cross-section, and we use the optical theorem to do that. The total cross-section is a fundamental parameter of the strong interaction, and its evolution with the energy is an interesting topic. So the way we do the measurement is represented up here. So we measure, so the optical theorem tells us that the elastic cross-section at zero momentum transfer, extrapolated at zero momentum transfer, it can give us the total cross-section. If we look at the elastic cross-section as a function of TT, is the momentum transfer, okay, between the protons. So if we look at the elastic cross-section, it has two terms. One is the nuclear interference, and the other one is the Coulomb term, the nuclear factor and the Coulomb term. At the special optics, we have taken data of 90 meters. We are sensitive to this mainly in the region where this nuclear term is the dominant one. and it has a shape of this type. So what we will do is to measure the differential distribution as a function of t, determine this v parameter, and extrapolate to 0 t in order to measure the total cross-section. So the momentum transfer is measured through the angle that the particles, the protons are deflected. And we need to take into account also the optics of the beam through some matrix that helps us propagate the information of the angles to momentum. And so we use, in this kind of events, we have tracks back to back. Here we see the pattern. So on one side of the detector, it's the opposite to the other side of the detector. So, and we will be looking to events that are back to back like this. Here we can, here we can see the t distribution in this lower plot for data, and we see also the main backgrounds that are very, so you see the backgrounds are very small. We have a double Pomeroy exchange background in red that is estimated with Monte Carlo, and we have some accidental coincidence that could be due to beam halo or background, or and these kind of events are estimated with data, with a control region that basically will have a proton on one side, and on the other side the proton is on the same let's say both in the upper or both in the lower part of the detector. Okay, and with that we can estimate the background. So the acceptance we have is shown here in T. You see that our acceptance is relatively high for T's that go approximately in between 0.01 to 0.1 GeV squared. And but it keeps relatively large, still around 0.3 or so. And there are small differences in between the two arms. Okay, so we need to get an external luminosity measurement, and we use Van der Meer scans for that. They were calibrated at 10 to 13, and they have to be extrapolated to the luminosities at this run we had. And this extrapolation is the dominant component of the precision, that is 1.5%. So the cross section as a function of t shown in this plot on the right. Okay, first the second so the beam energy and the luminosity both are the dominant systematic uncertainties in this study. So here we see the cross section as a function of t, and in red we see the elastic fit to determine the nuclear slope, that is this v parameter. And with that, we can calculate the total cross-section that we see here. So actually, we can calculate the elastic cross-section and then extrapolate using the theory to obtain the total cross-section. So we see here the results, and it's better to look at the plot as a function of the square root of s. We see here measurements done by other experiments. The atlas ones are in red, totem is shown in green. Okay, you see, okay, we are close to in agreement in both cases, and this is the elastic cross-section. With this, we can also calculate the inelastic cross-section as a difference between these two, okay? The inelastic cross-section can also be compared with other measurements, and here we have not only measurements from other experiments, but also other measurements done by Atlas with other methods, only with the central detector that is sensitive only to the inelastic part of the cross-section, not to the elastic one. So the systematics are quite different. So the measurements with alpha at these squares, and you see they have much better precision than the measurements done with the central detector only. And they are at 7 and 8, okay, 7 and 8 TeV, and it will be interesting to have a measurement also 13 TeV that we have the data, so it needs to be analyzed. And this will help reducing also extrapolation uncertainties to energies such as the energies of Auger. Okay, another kind of diffractive physics is the differential distributions in single diffractive events. So this is one of the results we have obtained recently. So diffraction is important to understand things like such as the low X proton structure, but it's also interesting for cosmic ray showers to study the evolution of the shower, because the diffractive cross-section is one of the parameters that influence the way the shower evolves. From the point of view of the LHC, it is very important for the pileup modeling to study the number of tracks and distributions in the pileup events. So phenomenologically, this is described as through the exchange of apomero, and the models have very large uncertainties, as we will see in a moment. So, okay, maybe I change directly. The previous measurements done in Atlas were done using only the central detector, no forward proton tagging. Therefore, they had some difficulties in distinguishing events of the type of the single diffraction and double diffraction that we see here in the central picture. So if we look at these distributions, this is the cross-section of the events as a function of the rapidity gap. Rapidity gap is the distance with no activity in the detector, in eta. And we see here, so data is shown in blue, and we have two different Monte Carlo prediction, Pythia 8 in the upper plot and Foyet in the lower plot. The blue part is the non-diffractive component. And then we have single diffraction in red and double diffraction in green. And what you can see in both plots is first that the Monte Carlos do not agree with the data in the shape at all. But not only that, both Monte Carlos predict very different fractions of single and double diffractive events. And therefore, if we really want to understand what is happening in here, we need to tag these forward protons to distinguish these components. So we have done that already at ATEV. And so the measurement consists in identifying a proton in alpha and looking for activity in the other side of the detector, as we see in this sketch, okay? So we use data taken in 2012 at high beta star. And in alpha, we can measure for momentum transfer, that variable t, and also this variable chi, that is the missing mass, or basically fractional missing mass squared. So the invariant mass that the protons basically left, and that goes into the central detector. Okay, for the measurement we use for the energy loss we use a measurement from the inner detector that provides a bit better resolution at low chi, because at low angle the resolution in alpha becomes worse. So the backgrounds we have are central diffraction, but we also have some accidental coincidences of diffractive events and some central activity that could come from beam background or some pileup. So we model those with data-driven techniques. First, we estimate the probability of accidental proton coincidence, and then we use a validation region in which we have two protons on both sides of the detector, on both sides of the central detector. So as you see in this schema, in the left and right side arms of the alpha, in addition to the activity in the central detector. And with this, we can see that, so the lower plot is in the validation region. You see we have a good agreement of the simulated background with the data. The upper plot shows the distribution of the chi variable, in the end logarithm of chi in alpha, in the signal region. And here we have in green the single diffractive events that had to be normalized renormalized with respect to the PCA prediction in order to match the expectations in data, but we see that the shape is rather okay, rather well reproduced by the simulations. So the dominant systematics depend on the variable we are studying. In the case of the chi distributions, hadronization and overlay background are the dominant uncertainties. And in the case of delta eta, we have, for low delta eta, we have the overlay background, but for high delta eta, the normalization of the central diffractive component is one of the dominant ones, okay? So we have here the delta eta, so the distribution of the diffractive differential cross-section as a function of the rapidity gap, shown here in between the proton and the activity in the detector. Compared, so the data is compared to 3 different Monte Carlos, PCA8 with 2 different models, A3 and A2, that basically contain different properties for the Pomeroy interaction, the description of the Pomeroy interactions, and Herbig 7 that is more similar to PCA3 but has a different particle dissociation, final state particle dissociation model. The first thing we see is that the 3 Monte Carlos overshoot the data, so the normalization is off by quite some large value. Smaller, so the agreement is in the normalization is better for PCA8 than for the other 2. However, PCA2 seems to be the one that has the flatter distribution with respect to the data. There is a bit of a slow, inclination here for the other models. So this data can be used to tune the Monte Carlo models and improve the Monte Carlo predictions. So we also did a fit of the nuclear slope with this data, and we see it here. And the agreement between these A2 and A3 models is shown here. We have, so agreeing within 1.6 sigma with A3 and 0.5 sigma with the A2 model. Here we see also the measure, so some measurements from CMS in comparison with Atlas as a function of log of chi, and we see that we have complementary acceptance in chi, Atlas and CMS. So I move now to the intermediate process with intermediate cross sections, such as central exclusive dijet production. And okay, so these kind of processes are quite interesting. We basically have 2 protons that are intact, and there is an exchange of gluons that we see here that produce. They can produce different particles, even the Higgs boson there, but what we'll study first is the production of jets here. And this gluon here ensures that there is no color exchange between the protons. So these 2 jets are the only activity in the central detector. There is no proton remnants, other proton remnants anywhere, okay? And this is different, for instance, from the other diffractive events where you can have some other remnants. So the central exclusive production, the cross-section is a bit lower, so it needs high luminosity. We need to measure proton kinematics. So we will also use this chi, that is the fraction of energy lost by the proton. And we will need to use also the time of flight measurement to suppress background. And this will be very important to suppress the accidental coincidences. So how does the time of flight help us? So if we measure the arrival time on one side of the detector for the protons and the arrival time on the other side, the difference of this arrival time multiplied by C will give us a set vertex position. And therefore we can match the vertex position of the protons in AFP with the central detector, so with the vertex position of these 2 jets, and this will help us clearly reducing the background. In addition, the kinematics of these 2 protons should match perfectly well the kinematics of the jets, and therefore, and this is also one of the properties we will use to clean up the events. So we see here some distributions. So these are not yet with data, so they are predictions for what we will be obtaining with data in the future. Here we see, for instance, distributions of the difference in their kinematic properties measured. So this plot in the center is the rapidity difference measured for the dijet system in the central detector, and the expectation from the protons measured with the protons. So for exclusive events, we have they are very centered into 0, and they match very well, basically. While for the other backgrounds that include double Pomeroy exchange, single diffractive events, or non-diffractive events with accidental coincidence with protons, they are very different. Here we see also the mass, the invariant mass of the central jets with respect to the invariant mass lost by the protons. And we see that for exclusive jets, they peak at 1, while all the other backgrounds peak at much lower values. The time of flight measurement is delta Z between the vertex measured with the jets and the vertex measured with AFP, shown in the upper plot, and this is fundamental to reduce the background accidental coincidences. And you see here, okay, exclusive jets, this is very peaked, while accidental coincidence, non-diffractive events, and single diffractive events, they are very wide. Okay. Okay. This it's important to notice that this central exclusive production requires special triggers. We cannot, most of the other physics topics we have seen, they rely on central detector triggers, okay? However, central exclusive production, they cannot rely on that because for the dijet triggers, we have huge, typically huge prescale factors. We have a huge cross section, so we don't need to keep them all. And therefore, we need to really look for those that have protons in coincidence. This is another of the Portuguese contributions we are working on, and that will be used for the round 3. And basically, what we need to do at level 1 is require the protons are identified in the time of flight detectors, and they are in coincidence with jets in level 1. This is not sufficient, and we need to design dedicated high-level triggers that match the kinematics of the jets to the proton kinematics, first using the tracking system, and afterwards using also the time of flight measurement and vertex reconstruction for the dijet system. We do it in 2 steps because the first part is faster, allow us to reduce the rate already significantly, and then we can run the tracking that is more time consuming. So this is some work that is being done currently in Muíño, and will improve, will prepare the measurement of the central exclusive production in Atlas for the round 3. So the expectations are shown here for, in this case, this is 40 inverse femtobarn with mu equal to 23, okay, low luminosity, as the one we had before in round 2. And you see here, first in green, the dominant background is non-diffractive events with accidental coincidences. And in yellow, we have the expected exclusive jets. Here we see the background subtracted plot and the size of the uncertainties we expect. If we go to high luminosity, 300 inverse femtobarn and higher mu, 46, we see that the non-diffractive component increases significantly, and therefore increase the uncertainties. This means that we will need to improve the measurement, and in particularly time of flight detector is very important, and the resolution in the timing, and we need to reduce also this the background as much as possible. However, we see that we can, we expect to be able to do the measurements with the data to come. So on the diffractive area, there are still a lot of physics results in the pipeline that we will see in the near future. We have the studies of diffractive jets with alpha, charged particle distributions, single diffraction at setting TeV, exclusive dilepton production, exclusive pion production, strange production in diffractive events, and more results to come. So if you're interested in this kind of physics studies, you can stay tuned, or if you are really interested, you can come and work with us on some of these topics. I take the chance to say that the diffractive, so the forward proton community in Atlas is really small. So any person that wants to come and join us in this effort is really welcome, because they will make a difference. I move now to another kind of topic. So up to now we were in what Atlas normally calls the bread and butter physics, because with relatively low luminosity we can do it. And now we go to the one that is okay, more exotic, or a bit requires already high luminosity. And I will start with the quartic gauge boson couplings. So the idea is to, as I mentioned before, is to study photon interactions, and the nice thing is that the forward proton taggers transform DLH in a photon-photon collider. They allow us to study photon collisions in a much cleaner way than with the central detector. So we will tag intact protons, and then we have so interaction of two photons, and here in the central system we may have either W sets or photon pairs or whatever we are interested in studying. And the idea is that the electroweak symmetry does very precise predictions of what we can measure and what we cannot measure, and also the value of the cross-section expected. So we expect to have the symmetry allows to have quartic W boson couplings, gamma gamma WW, WW Z Z, but no quartic Z boson couplings or gamma gamma Z Z at 3 levels. Sorry, they can only happen at the loop level. So, however, physics beyond the standard model, they may modify these expectations, and therefore it is very interesting to study this kind of processes. Since we have an exclusive process here also, we can match precisely the proton kinematic information to the central detector information. And this allows us to clean up all the background significantly. And we will also need to use timing information to reject the pileup. Okay, we have access also to triple gauge boson couplings of this type, but today we'll focus more on the quartic ones, okay? So, the measurements have not yet been done, they are to be done, and so we'll present some phenomenological studies. We'll start with four photon interactions of this type. So the idea is that if we have new physics at a mass scale that is much larger than the one accessible at the LHC, we may observe this physics as an effective interaction. That would happen in loops here, but we would see it as an effective interaction. Therefore, what we will be looking at is we introduce new operators in the Lagrangian that will represent how we see this interaction at our energies. The lowest dimension operators we could introduce in these 4 photon interactions are dimension 8, and they are these two represented here, that would require anomalous couplings. So if in these loops we have charged particles, the interaction is proportional to the charge to the force. So some models, such as composite Higgs models, foresee particles, leptons that have charges larger than 1. And therefore this cross-section, for instance, could increase considerably. Other models, such as extra dimensions or strongly coupled conformal theories or so on, predict cross-sections that are the order of 10 to the minus 13, 10 to the minus 30, couplings, 10 to the minus 13 or 10 to the minus 14. So if we measure precisely this process, we could be reaching this precision. There are plenty of backgrounds. First of all, we have possibility of diffractive events in which we have an interaction here where we exchange quarks, leptons, or W bosons. We could have central exclusive diphoton production. central exclusive digest mix identified as photons, or even non-diffractive photon production in coincidence with proton interactions, or even digest production in coincidence with accidental coincidence with protons. So these have been studied in a phenomenological study that I show here, and basically one can use the properties of these events, such as the very large invariant mass of the diphoton system, to reject the backgrounds. Here we see, for instance, in the case of anomalous couplings, we would have very large invariant masses that go, okay, start from 500 to above, while the backgrounds are at low mass. Here we see also the acceptance of AFP. That depends on the beam optics and how close we get to the beam, and it goes up to B or so. In addition to that, we can measure also, match the kinematic properties of the protons and the photons. For instance, this is the missing mass of the proton system with respect to the diphoton system, and of course for these exclusive processes, and in case of photons we have very good mass resolution, so we have a narrow peak with respect to a very basically flat background. So with this we can clean up the events, and the expectations, okay, depend on how we do the analysis, but let's focus, for instance, in this column. This is 300 inverse femtobarn, and it shows the exclusion limit at 95% confidence level. And we see that we can exclude the couplings that go up to 10 to the minus 14, 10 to the minus 13. Therefore, we are reaching the sensitivity to the extra dimensional models we will be reaching. Okay, with okay, and they could be eventually done at high luminosity. With higher pileup. Okay, same kind of studies can be done for photon WW and photon ZZ. In this case, the Lagrangian operators we could access are dimension 6, shown here, and we have the anomalous couplings for W's and for C bosons. Okay. So this is another phenomenological study that was done for the AFP technical proposal, and we see here the sensitivity we can reach. And this is the exclusion limit, goes to these couplings of the order of 10 to the minus 6 that reach the sensitivity also of the extra dimensional models. They also improve the results that are expected with the central atlas detector by 2 orders of magnitude or so. So for completeness, I want to say the CMS has already used some of their forward proton tagging data from, I think, 70 eV or 80 eV to measure to this process, and the limits they have obtained, they are at the order of 10 to the minus 4, as you see here in these couplings. We can also search for exotic physics, and one process we are interested in Portugal is the flavor changing neutral currents in top quark production. So if we look at flavor changing neutral currents in the standard model, they are strongly suppressed. Here we see a table from Atlas, results in which we have participated, where we see several different top decays. And the predictions for the standard model are shown in black here. So this is the branching ratio. They are really small. And but however, beyond the standard model processes such as the MSSM or parity violating models, two Higgs doublet models, and so on, predict branching ratios that are much higher than this. And you see here some of the theoretical predictions. You see here also Atlas in blue and CMS in red measurements, not limits on these couplings that have been obtained, and we are okay. We are already starting to exclude some of these models, but it would be very nice to improve the exclusion limits on those. one process that can be used to help in these measurements is the single diffractive top quark production of this type. So produced through the interaction of a photon with a new quark, and we would have a top here. And this process would help complement the measurements that are done only with a central detector. It could help improve the measurements with very different process that has also very different systematics. And this is one of the processes we're interested in and we will be working on. In addition to that, we have many possible exotic particle searches. I will talk today about the dark matter search. This is quite interesting because this is a model that will be very difficult to observe in the central detector only. Some SUSY scenarios, like this compressed SUSY mass scenario that is favored by some cosmological observations, predict very small mass splitting between the neutralino and charginium. So we would have a decay of this charginium to a lepton and a neutralino, and this would be characterized by very low momentum, very low transverse momentum, and very low missing ET also. Therefore, the events are very challenging with the central detector, but they can be done with the forward proton tagging. And here we see another phenomenological study done to identify this kind of processes. Basically, here we have the two protons with very good mass resolution that would allow to measure the mass of these charginus. And in addition, the protons give us clear signatures that we could use to identify these processes. So the lepton momentum would be between 5 and 40 GeV. It cannot be too high because then the background from W boson production would be very large, and they go as far as 5 GeV. To have in addition, we have we can use the missing mass as a discriminating variable that would help us reduce some of the diffractive backgrounds, also such as WW diffractive production, and also other properties of the lepton, such as the acoplanarity that reduce other kind of exclusive lepton production and exclusive kaon production. So in the end, here we see 300 inverse femtobarn, for instance, with 50 collisions per bunch crossing. We can reach a number of events that is for the signal that is close to the number of events expected for the background. And therefore we expect to be sensitive also to this kind of processes. However, this kind of processes, they need dedicated triggers because we cannot rely on this very low lepton momentum with the central detector only. And this is another area where our group is interested in, and the kind of triggers we have been developing for the central exclusive production will also be very interesting. Can be implemented with low PT leptons and such that we can also search for this kind of events. And for this, we are looking for interested students that would like to study this kind of processes and could contribute to these studies. So I come to my conclusions. So I hope I have convinced you that the forward proton tagging enlarges the physics capabilities of ATLAS, not only with single diffraction, with diffractive physics events and topics, but also with a variety of other topics, such as search for anomalous quartic gauge boson couplings and search for new physics in diffractive events. The Portuguese ATLAS group has contributed to the preparation, to the construction, operation, and of the ALFA and AFP detectors, and we are now starting to work towards the physics topics. So the preparations for the run 3 are ongoing, and we expect to have a wealth of data in the near future. Near future means during the run 3. As I mentioned before, the forward physics group at Atlas is very small, and therefore more people would really make a difference. If you are interested on this kind of physics, please come to us. So, okay. Oh, I forgot. Thanks. Thank you very much. I don't know if you have questions or comments.
Yes. Thank you very much, Patricia, for this very nice seminar. Now, for the questions, what I propose is that you use these, you have there an option to raise your hand and so that we can organize. So who wants to go first? Questions?
Well, maybe, okay. You can also
yeah, or just talk. If you don't find the button, just talk.
Yeah, don't say. If there are too many people at the same time, we will handle it. But don't be shy.
Okay, so some questions for Patricia? Okay, I have one. If just to start, just to break the ice. So in your slide 21, Patricia, when you show the cross section, the total cross section.
Mm-hmm. Okay. Yes.
So you said that the results are sort of compatible with totem, but I see the ATV point. It's a 2 sigma.
Yes.
Totem is doing a total cross-section measurement, so it's measuring the elastic channel and the inelastic. While you're saying that you just measure the elastic. Is that so, right?
Totem measures the elastic cross-section, I think, also, but with a different method than us. Yes, for the total cross-section, I think they measure also elastic cross-section, but with a different method.
Okay.
Okay, I'm not 100% sure about how they did their measurement. I cannot tell, but I think these measurements were also done. Okay, I mean, they may have more data to improve these measurements.
Oh, okay.
But I'm not sure.
Okay.
I'm 100% sure. But they use a different method. This is for sure. Actually, there could be systematics also, because there is this extrapolation in here that enters, and this could also be the reason why we get different. So we have this extrapolation uncertainty because going from the elastic to total cross-section, this comes mainly from the theoretical expectations.
Patricia, I have a question regarding the expectations for run 3. I don't remember which slide that was. And so I was just wondering, that is probably depending on the time resolution that you have achieved in your timing detector. And I was just wondering, what is the time resolution that is assumed?
So I in the results I presented today, in all the studies, they assume 10 picoseconds resolution. As I said, we obtained already 20 picoseconds in the measurements done in 2017 with the time of flight detectors before the problems with the, well, actually even during the problems with the photomultipliers, because we had very low efficiency, but we had very good time, good time resolution. We expect to, so for the run 3, we will be changing the Pico TDC. And this will have a much better resolution. So they have been developing a new Pico TDC, Alberta University, and this will reduce the resolution of the component that goes to the resolution of this Pico TDC is currently, I think, 17 picoseconds, and will be reduced to 3 picoseconds. So we expect to be able to get something closer to 10 picoseconds resolution.
So the 20 picoseconds that were achieved is a follow-up. Is it something that was achieved with colliding beams in the test beam?
Yes.
Or
yes.
how?
No, in test beam, of course, but also with data taking proton data in Atlas. So with the Roman pots, as the configuration I've shown before, I can go up. Basically, okay, this configuration will have time of flight and silicon tracker detectors, and we use, like it looks here, these 3 bars, are shown here with the groove and so on. So we had problems in the detectors I mentioned before due to the photomultipliers and also some glue that we used here in between the bars that lost transparency and therefore affected the efficiency, but did not affect the timing. The timing measurement, and we did the measurements with the data that we could trust, and we get 20 picosecond, 25 picoseconds resolution per proton.
Very well. Any more questions to Patricia?
Patricia, this is João. Just one question that I was interested from your presentation. If you have any prospects for measuring central exclusive Higgs with your setup.
Higgs cannot be measured with this setup, and I will show you why. So let me go. So you see here the acceptance, okay? You see that we have acceptance for masses greater than 200 GeV, okay? Central, so the mass produced in a central system. In order to be able to have acceptance for central Higgs exclusive production, we would need to have another station of forward proton tagging detectors that would be 400 meters from the interaction point, so 200 meters farther down from the beam, from these ones. And this is a very tricky part of the beam pipe. It could not be done with Roman pots like this. They needed a movable beam pipe that would get closer to the beam. It was never, so we never, let's say, since the community of the forward protons is small, we have focused first on these the closer stations that were simpler to implement. We basically had no time yet to work on the other ones. So although those are much more tricky and they would need to be, the solution for technical solution for that would need to be worked out with the with technical staff from the beam. There were some proposals done in the past, but okay, the physics program was accepted with this closer station. There is still a chance that they will be, I mean, that there will be work done towards the other station, but for the moment we have been focused on that. And this, if this works, okay, we will see the rest. But of course, the Higgs was one of the motivations, for instance, that attract me personally towards this. Nowadays, the measurement of the, let's say, of the spin of the Higgs is not so, I mean, this process, okay, it's still interesting, but not so much as the very beginning. Because we have measured, we can do a lot of measurements with the central detector.
Okay, thank you.
More questions? Okay, there doesn't appear to be more questions, at least for now. Okay, so I would like to thank Patricia for accepting this invitation, and the slides will be at the Indicos page as always. And if you have any more questions, you know Patricia, you know her email. Be sure to contact her about this very interesting program.
Yeah, and if you are interested on working for something like this, please get in contact with us.
Okay, thank you everybody, and see you next week where we have another seminar already scheduled. It's going to be Pietro Muíño. And thanks a lot for being here. Stay safe.
Thank you very much. Bye-bye.